Welcome! We're Group B and we're happy to tell you all about our final PSR design in this final presentation. First of all, we want to talk about the project launch, when we came up with several ideas on how we could approach this problem. We had very different ideas, from gator skin balls over drop-like designs, parachute designs, rocket-like features, and others. We talked about those designs in a group and assessed them by using different matrices, such as the conceptual design screening matrix. We talked about the different designs and came up with 3 designs that we wanted to move forward with. After identifying these designs, we weighted the criteria to identify the most important one. Then in our final concept design selection, we chose one final design that was, from our point of view, the best one for this problem. But we did not just come up with one specific design. We made a whole criteria table that gave us information on what specifications our design should include. For example, for the orientation, we wanted a bottom-heavy design with an aerodynamic approach. To slow it down, we tried to increase the surface area. The lattice structure inside should help absorbing the impact energy. Divided spaces for the Pixy Stix should increase the strength of the structure as well. And we tried to incorporate a pin-to-lock mechanism for the container that includes the Pixy Stix. What you see here is our first prototype that we built for this class. You can clearly see the rotors, a spring mechanism on the bottom, it's kind of cylindrical, and a lattice structure inside. Now Ali will tell you everything about the DFAM and MFAM process.
Our design process went through 3 main stages. In the first stage, the focus was only on DFAM. As Christian mentioned, each one of us came up with unique design that leveraged DFAM opportunities. At this stage, we mainly utilize DFAM opportunities for saving weight by using lattice structure, combining functions like the impact absorption as well as containment of the Pixy stick, and internal features like using air channels inside the container itself to slow down the speed of impact. In the next stage, we included MFAM as well as DFAM. When we added MFAM in the process, the designs became less unique than only DFAM, as you can see here and compare. That's because we all tried to find a balance between the opportunities and limitations of additive manufacturing. This resulted in simple designs that met the requirements part functions actually, while at the same time taking into account factors like build layout, support structure, design guidance, and post-processing. We arrive at the final design by integrating different factors, such as our prior DFAM and MFAM experience, the class feedback, and our group discussion.
So our PSR final solution is comprised of 4 unique custom design parts and 2 COTS parts. On the left here, we have the assembly of the full system, and I'm going to go into detail a little bit about the parts themselves. The 4 custom parts, we have the base container, which is the Fusion 360 design, which we use to hold the Pixy Stix, and this is the design that gets fed into NTOP for lightweighting. We have the lid that bolts to the top of the base container, which we use to hold in the Pixy Stix. We have the propellers, which mount on the bolting points, and we use these to help slow down the container so it doesn't impact the ground as hard. And then we have 3 of these spacers, which we use to help attach the lid and the propellers onto the container. Now, for the general shape of our Pixy Stick container, we use the geometry of one of our original CDR designs as the starting point for our PSR container. Now, what this design features is a primarily cylindrical body that tapers down in the bottom and has a wider base. And the idea is that this wider base would be weighted, whether it was with a gradient lattice or an actual physical weight inside of it, that would help orient the payload so that way it fell on the base. And then we also had this payload or this container include 3 channels for Pixy Stix. Now, our logic here was that we wanted to make sure that the samples were protected. And we wanted to make sure that in case one of the samples happened to break, maybe it was a faulty Pixy stick or maybe it was due to an impact, that if one of the samples broke, it wouldn't contaminate the rest of the samples. So essentially what we're envisioning is that a third of the samples are going to go in each of these channels. And if one becomes compromised in that channel, we still have 2 other channels that will be protected in the sample. All the samples will not be ruined. Now, it would have been best if we had essentially a single channel for each of the Pixy Stix in this whole body here, but due to weight constraints, that wasn't feasible. Now, what we did with our design was we targeted it with 3 bodies, and these 3 bodies would help us better understand, or it would help us better visualize this and modify the design end top. So the first body we started with was this outer shell here. And the idea was that this outer shell could be used to surround the lattice. It could be used as kind of an impact point if we wanted it to be. We ended up not using it for this design, but we wanted to have it in there just in case in the CAD. The second body that we have is essentially the lattice body itself. And so this is the block that we're going to use end top to turn into a lattice. And then the third body is the Pixy stick channels themselves. And so these are the 3 cylinders where the Pixy Stix will go. And something that we added in were these latch points, one of them being on each of these containers. So 3 bolt points. So that way we could screw the lid into the top and cap the Pixy Stix in there. Now, as this design serves as part of a system, it's a multi-part system, we had to think about how all of it was going to work together. We had to think about tolerances. How are we going to access bolts? How are we going to tighten bolts? How are we going to be able to insert the Pixy Stix in? So we needed to think about how the system could work once we put it into end top. Now, for example, the first generation of this CAD design, it didn't have these latch points in here. And we were thinking that essentially we would use a wire and attach the lid directly to the lattice. But after some consideration, we thought that a fixed structural point may be better to help hold the lid on when impact. Now, given that end top is used to primarily modify existing designs and not create new designs, we had to build these tolerances into our original CAD in Fusion 360 so that way we could have the capability to use this whole thing as a system. So some examples, I'm going to go to this sketch right here. One of the examples is that we wanted to make sure that we left enough room around these notches so that way we could easily get the bolts in. So for example, we left around a 2 millimeter clearance on both sides of these these notch points here. And so that way we could easily get our hands in there and attach the bolt, and we didn't have to worry about accidentally damaging part of the structural lattice with that clearance. So that was one thing we did. Another thing we had to do with the Fusion 360 design was that we had to build in a tolerance to account for the 20 millimeter bolt that we have. So essentially the bolt is going to slide in here, and then there's a spacer that goes here, and then the nut goes down here. And so we wanted to make sure that this cut was deep enough so that way when we put the bolt inside, it doesn't puncture or penetrate the lattice and cause any structural instability. Now, the last thing that we had to do was we had to make a notch in this outer body, the shell of this design. So that way we could easily get in there and hold a pair of pliers so we could attach the nut to the bottom of the bolt so that way we could get the spacer in here. Now, at the point, we didn't know if we were going to have an outer shell or not, but we wanted to make sure that it was safe and we had the room just in case we decided to do that.
Our final PSR solutions incorporates a cutting-edge lattice design By implementing a body-centered cubic lattice structure with a uniform cell diameter of 8 by 8 by 8 mm, we achieved a balance between lightweight properties and mechanical strength. Throughout the design process, we use NTOP software to engineer and iterate on the lattice design configuration. We experimented with different lattice types to tailor the structure precisely to the requirements, eventually selecting a gradient density approach. This method allowed us to vary the beam thickness from 1.5 mm at points of lesser stress to 1.1 mm where greater stress resistance is essential, enhancing durability while minimizing mass. The resulting structure optimized for both performance and weight, weighs only around 264 grams. The integration of lattice design not only enhanced the product aesthetic, but significantly improved its functionality by combining lightness with durability.
In order to hold the Pixy Stix inside the PSR container during the launch, but also allowing us to place and remove them when we wanted, we created a lid that would go on top of the PSR container. Originally, the hole had 6 lids for connections. The inner 3 would connect to the lattice structure with an aluminum wire going through the unit cells, and the outer 3 would connect using micro screws to the propellers above. However, in our second iteration, we revised this so that there would only be 3 holes in our design. This way, the micro screw would go through the propellers, into the lid, and into a connection outside of the lattice structure. This allows for a lighter design and a more simpler and concrete solution.
The proposed free-fall velocity reduction mechanism utilizes 3 propellers, each weighing 10.56 grams, attached to the outer frame of the lid. These propellers are designed to reduce the velocity of free-falling objects by generating air resistance during descent. The integration of an extended beam allows for secure bolting of the blades with the main lattice body, which is organically blended into the airfoil design. The total mass of the propellers amounts to 31.68 grams. This lightweight yet effective design enhances the object's aerodynamic properties, potentially slowing its descent significantly without compromising structural integrity or adding excessive weight.
To test our final design and connections between each of the pieces, we used the Prusa XL at the Learning Factory to print an FDM PLA model. At 15% infill, the tray used 139.3 grams of filament and 15 hours, 5 minutes to print. The pieces fit together well using the micro screws purchased at Ace Hardware to combine them. After assembling the parts, we threw them off of the top floor of the west parking deck next to the Engineering Design and Innovation building, and made sure that the ground was clear of pedestrians. The launch was successful and the device functioned properly in that it spun and landed in the correct orientation. The propellers unfortunately did snap off during the landing, however the lattice structure remained intact. When printed in metal, we expect that this issue will be resolved fully due to the material's increased properties.
One, lunge!
In designing the lattice structure for optimal 3D printing efficiency, the build orientation is set vertically, thereby eliminating the need of any bridging or overhangs that could compromise the structural integrity. Propellers are strategically mounted on the thin airfoil sides at a precise 90-degree angle relative to the horizontal plane, facing the side devoid of grooves to ensure that no supports are required on the plane, streamlining the manufacturing process. This careful placement not only enhances aerodynamic performance but also optimizes the material usage, as evidenced by the overall print-to-part ratio of 1.015. This ratio indicates a highly efficient use of materials with minimal waste.
So, to sum up, the proposed design addressed all the requirements we shall meet, and it also exceeded critical design objectives like the total mass. We achieved 300.3 gram, which is 40% less than the required 500 gram mass. And we minimized the print to part ratio. We only have 1.019. We also try to minimize post-processing. We don't need a lot of things to do after printing. Also, the container is now easy to open. Like you only need hand tools to open that bolt and nut. And this is our design. Thank you for listening, and we are really excited to see the final print.